Okay, good afternoon. Let's start solving the questions. The session is recorded and will be combined with the morning session to add the problems that we could not solve in the morning. So let's start with problem 2027. Problem 2027 reads the following. An electron is moving to the right from position A with a speed of 1.43 10 to the power 6 meter per second as shown in the figure. At position A, there is an electric potential of 2.53 volts. When the electron reaches position B, there is an electric potential of 1.35 volts. What is the electronic speed as it reaches position B? So we have here an electron with a speed V1 and a potential of 2.53. At point B, the potential is 1.35 volts. We need to calculate the speed at point B. So we have V1 1.43 10 to the power 6 meter per second. M for the electron is 9.11 10 to the power minus 31 kilograms. Charge is minus 1.6 10 to the power minus 19 coulombs. We need V2. We know V1 potential 2.53 volts and V2 1.35 volts. So where do we start from? We know that delta U equals to Q delta V, and this is minus delta EK. So we have Q delta V equals to minus half M V2 squared minus half M V1 squared. If we take half M outside, then we have Q delta V equals to half M V2 squared minus V1 squared. Then V2 squared minus V1 squared equals to minus 2Q delta V divided by M. And if we substitute, V2 squared minus 1.43 10 to the power 6 squared equals minus 2 times minus 1.6 minus 19 V2 minus V1, which is 1.35 minus 2.53. Any question about this problem? If no questions, then we can move to the next problem. Next problem is 2078. 2078 reads the following. In an oscilloscope, an electron is accelerated from rest through a potential difference of 1.1410 to the power 3 volts. It then passes through deflecting plates that are 2 centimeters apart, across which there is a potential difference of 412 volts, as in the figure. The electron enters the plate region with a velocity that is perpendicular to the electric field of the plates. When the electron leaves the plate region, what distance will it have moved toward the positive plate? So we need to first accelerate the electron, and then let this electron enters the deflecting plates. Due to the electric field, the uniform electric field between those two plates, the electron will deflect. We need to calculate the amount of the deflection that's going to happen in the y direction. So this is 4 centimeters. This is 2 centimeters. Delta V here, 412 volts. Electric field will be pointing in this direction. Electron will be entering here, coming with its initial velocity, starting from rest. So let me call this one V1 0. V2, I don't know. Now, once this enters the electric field, there will be force, electric force in this direction. This electric force in this direction will cause the electron to deflect. I want to calculate the delta y. This one I'm calling also delta x. So what's going to happen here, I have an electron. This electron, I applying some kind of electric field on it to accelerate through the potential difference that we talked about. So there will be a potential difference between this point and this point, such that delta V here is 1.14 10 to the power 3. Here, positive, and here is negative. We're accelerating this electron such that this electron is picking up a speed, reaching to a speed right at this point before entering into the deflecting plate. So in order to get the delta Y, I need first to get the speed of the electron right at the beginning here of the field. So how do I do this? Again, delta U equals to Q delta V equals to minus delta EK. So I need, if this is, we said V1 equals to 0 at rest, then I know that Q delta V equals to minus half M V2 squared. Why? Because the V1 is already 0, so I need to calculate this V2. So V2 squared is minus 2Q delta V divided by M. V2 squared is minus 2 times minus 1.6 to the power minus 19 times 1.14 10 to the power 3 divided by the mass of the electron, which is 9.11 10 to the power minus 31. V2 squared is 414. V2 is 20.011 10 to the power 6 meter per second. So this is the V2 along the x-axis. Now I need to calculate delta Y. So in order to calculate delta Y, first let me calculate the acceleration caused by the electric field or the force exerted on this electron due to this uniform electric field. I know, number one, the electric field is V over D, 412 divided by the distance here, 2 centimeters. Then I also know that this force is MA, and here it's Y pointing in the positive direction within the same direction of the force. And I also know FE equals to QE. So by equating those, I get AY equals to QE over M. So AY is QE, which is 1.6 10 to the power minus 19 times E is V over D, which is 412 divided by M is 9.11 10 to the power minus 31 times D here is, so this is E, then AY is 3.62 10 to the power 15 meter per second squared. This is AY. Now, you can use the kinematics to calculate the total time this electron takes to go through the whole field. We know delta x equals to 4 centimeters. And we also know that x equals to x naught plus v naught t, right? So where x minus x naught equals to v naught here as v2, the one we just found. This is my initial. So delta x equals to v2 t, and t is delta x over v2, t as 4 centimeters divided by v2, which is 20.011 10 to the power 6, t as 2 times 10 to the power minus 9 seconds. So this is the time. Now, again, from the kinematics, I can find the delta y, which is y equals to y naught plus v naught t plus half a t squared. Now, when it comes to the y, and let me draw it here to make it clear to you. Right at this point, that has the force Fe and the velocity v2. This is on the x-axis. For the y-axis, I have Vy naught being 0. Because right at this point, along the y-axis, the velocity along the y-axis was 0. Then it will start to increase, starting from the moment the electrostatic force was exerted on it. So here I have Vy naught equals to 0, which is, in this case, this is going to be my Vy naught. So now this is going to be 0. So if I take y naught to the other side, it becomes delta y equals to half. A is ay, and then t. I need delta y, which is half times a, 3.62, 10 to the power 15, times 2 power minus 9 squared. In this case, delta y as 7.24, 10 to the power minus 3 meters. Any question about this problem? So what's happening here is, due to this force, start to result into an increase in the velocity along the y, and this one is going to deflect this way. Right at this point, when the electron leaves, you have to make sure that you know what's happening. This V2 is going to stay the same. And now you have Vy. And remember, the total velocity would be using the Pythagoras here. V equals to Vy squared plus Vx squared. They did not ask us to find the total velocity, but this will be the magnitude of the total velocity right here. Any question about this problem? Okay, so let's move to the next question. Next question is from Study Guide 6. In Study Guide 6, question number 1 reads the following. So this is Study Guide 6, Self-Test 2. Sorry, Study Guide 6, Self-Test 5, question 1. A proton in a particle accelerator increases its speed from 2.1 10 to the power 6 meter per second to 2.5 10 to the power 6 meter per second. What is the potential difference the proton moved through? Include the sign in your answer, and remember that potential is measured in volts, which is joules per coulomb. Okay, so drawing this, so we have a proton A plus with a speed V1, and then using particle accelerator, this proton achieved V2. The potential here was V1, the potential here is V2. So we have the mass for the proton as 1.7 10 to the power minus 27 kilograms. We have the V1, the speed is 2.1 10 to the power 6 meter per second. V2 as 2.5 10 to the power 6 meter per second. Delta V is what we need to find. Okay, so in this case, we have delta U equals to Q, delta V equals to minus delta EK. And here, delta V becomes minus 1 over Q half M V2 squared minus half M V1 squared. Delta V is, take the half M outside, minus 0.5 M over Q, V2 squared minus V1 squared. Delta V is minus 0.5 times 1.7 10 to the power minus 27 divided by 1.6 10 to the power minus 19. V2 is 2.5 10 to the power 6 squared minus 2.1 delta V becomes minus 9.78, or V2 minus V1 is minus 9.78. 10 to the power 3. Okay, so let's move on to the next question. Study Guide 6, Self-Test 5, Question 3. The question reads as the following. An electron that has a mass of 9.11 10 to the power minus 31 kilograms has a speed of 2.3 times 10 to the power 6 meters per second and is at a point where the electric potential is 4.8 volts. It travels a certain distance and its speed decreases to 1.9 10 to the power 6 meters per second. What is the electric potential at this point? So here the speed decreases. So we have an electron with a speed V1 while the potential is 4.8 at this location. And here the speed decreases, V2, such that we don't know V2, such that V1 is 2.3, V2 is 1.9 meter per second. The mass of the electron is 9.11 10 to the power minus 31 kilograms. We need to calculate the potential. So again, we know delta U equals to QV, Q delta V minus delta EK. We need to calculate V2, so we need delta V, that is minus delta EK over Q, or delta V is minus 0.5 M, V2 squared minus V1 squared over Q, delta V is minus 0.5 31, V2 1.9 10 to the power 6 squared minus 2.3 10 to the power 6 squared divided by Q is minus 1.602 minus 19. Then delta V becomes minus 4.783, or V2 as V1 is minus 4.7, or V2 as V1 minus 4.783 D2 is 1.725 10 to the power minus 2 volts. V1 is given to me 4.8. Any question about this problem? No questions? Then we will move to the next. Next is question 2164. Question 2164 reads the following. In the circuit shown in figure 2161, the battery maintains a constant potential difference across its terminals. The bulbs are all identical and are initially lit. In the parts that follow, in response to what happens, indicate whether the quantity increases, decreases, or unchanged. Explain each answer briefly. So let's first draw the circuit. Okay, so we have here 3. We have 2, 1, plus minus. This is A, B, C, and 4. Okay, so let's start with A. Compare the brightnesses of the bulbs initially. So what's going to happen in this case? We have identical bulbs, which means they are equal in resistance. 2 of them are connected in series. 1 of them is connected with them in parallel. In this case, those 2 that are in series will see the same potential difference across as this one that is by itself, which means here the resistance would be smaller in this branch than the resistance in the AB, which means this branch, the one that has the C, will withdraw higher current than this branch that has both of them. This is going to lead toward C being brighter than A and B. A and B would have the same brightness, so you can say A and B have the same brightness, which is less than C. So this is in terms of compare the brightness of the bulbs initially. And now we know We know why. Okay, so this is A. B, if bulb C is now unscrewed from the socket, what happens simultaneously to the brightnesses of the three bulbs? B. C will be off. It's switched off, right? Now A and B, they have the same brightness. And in this case, their brightness is not going to change. Why? Because the potential difference here is going to stay the same. The potential difference across this branch is going to be the same as before. So either I keep the bulb C or unscrew the bulb C, the potential difference across this branch is going to stay the same, which means that the current is going to stay the same in this bulb. So the brightness for A and B are not going to change. C is going to be off, and the current here will be 0. So I at the 3 will be 0. Do we have to answer for this as well? To the current, yeah. So the current at the 3 will be 0. Why? Because now the bulb is unscrewed. What happens to the current at I2? The current at I2, well, if I am to compare it with with item A, so let me go back to item A here and say that the current I3 here will be greater than I4. Why? Because the resistance in this branch will be less the resistance in the branch that has A and B, which means the current in 3 will be greater than the current in 4, and the current in 2 will be greater than all of them. Why? Because this is the total current. This total current I2 now is going to split into a current in 4, I4, and the current in I3. So I2 is the summation of I3 and I4, right? Now back to here, what's going to happen? I3 will become 0. What about I2? I2 will decrease. Why I2 is going to decrease? Because I3 now is 0. I2 was the one who was supplying I3 and I4. So if I3 becomes 0, then I2 now does not need to supply current to the bulb C. So I2 is going to decrease. What about I4? I4 is going to stay the same, unchanged. C. Bulb A is now unscrewed from its socket. Bulb C remains unscrewed. What happens simultaneously to the brightness of the bulbs and the currents at point 1, 2, and 3? So now we unscrewed bulb A. Bulb C remains unscrewed. What happens to simultaneously the brightness of the bulbs and to the current? So if this is unscrewed and this is unscrewed, in this case, I have broken the circuit from both branches here. And the current I3 equals to I4 equals to I2 equals to 0. There's no way the current is going to make a closed circuit here. All bulbs will be off because I have broken now the circuits. So all are switched off. D, with all three bulbs inserted in their sockets and lit, a wire of negligible resistance is connected from point 1 at the positive terminal of the battery to point 4. What happens simultaneously to the potential difference across bulb A? What happens simultaneously to the brightness of the three bulbs and to the currents? Okay, so now look what's going to happen. I brought a wire and I connected this wire from 1 to 4. What's going to happen? All the bulbs are back screwed in the circuit. However, I brought a wire I connected from between 1 and 4. Look what's going to happen here. Now this wire is going to make the potential of 4 equals to the potential of 2. Now they became one wire. And what does this mean? This means the potential here at 4 is the same as the potential at 2, which means the potential difference across the bulb A now is 0. So now if I am to redraw the circuit, I can redraw the circuit. The circuit is going to look like this. So this is B, number 4, 2, 1, 3, C. Right? Why? Because this light bulb, A, has been shortened out by this wire. The potential difference across that light bulb became the same. There is no potential difference. The potential difference is 0, which means no current is going to go through that. And this is what happens when I shorten out a component. So in this case, bulb A is off. B has the same brightness. I3 equals to I4 and would be equals to half I1 actually, because they are equal. Then the total current will be twice I3 or I4. Yeah. So any question about this problem? If no questions, then we can move on to the next problem. Next problem is 2171. 2171 reads as the following. Oh, sorry, 72. In the circuit shown in the figure, what is the power dissipated in each resistor and supplied by the battery? Okay, so here we have this circuit. Sixteen ohm, 16 volts, 32 ohms, 32 ohms. So where shall we start from? We need first to calculate the total current. And if we want to calculate the total current, which is this one, this is my total current, I'm calling it I. Then I need to find the equivalent resistance. The equivalent resistance is basically this 16 ohm that is in series with the equivalent of those two. So let me call this one R equivalent 1. And those are 32 over 32, 16 ohm. This is only used for two resistors in parallel. If there are more than two, we need to use the general expression. So the R equivalent 1 now is 16 ohms. Then R equivalent total is R equivalent 1 plus 16, that is in series with it. So R equivalent, the total is 32 ohms. So in this case, my current I is 16 volts divided by 32. I is 0.5 ampere. I found the total current, I. Now I can find the power dissipated into the 16. The power dissipated into the 16 is the following. I can find the potential difference here. So if this is plus minus, and I'm calling this one delta V1, then power 1 is delta V1 times I. Remember, for the resistor, the current enters the positive terminal, leaves the negative terminal. So P1 is delta V1 I. I don't have delta V1, so I can continue substituting. Delta V1 is what? Delta V1 is R times I times I. Then V1 is R16 times I squared, which is 0.5 squared. P1 is 4 watts. Now, how much is the power dissipated into both resistors? So if I come here and I say plus minus, this is delta V2. And this is delta V2 is the same across both resistors, the 32. How can I calculate this delta V2? If I want to calculate delta V2, I have to include all the resistors that are involved within this potential difference. So it will not be this 32 by itself, it will be the combination, which is the equivalent resistance of the two resistors that are in parallel. So P1, as I said, now let's say P2 equals to P3, they're the same, equals to delta V2 times the current, let me call this one I2. So P2 is delta V2 so let me find delta V2. Delta V2 is R equivalent 1 times the total current. Delta V2 R equivalent 1, which is 16 times I, which is 0.5. Delta V2 here is 8 volts. Now back to P2, I can say P2 is delta V2 times I2, and I know that I2 is delta V2 divided by 32. Then P2 is delta V2 squared divided by R. Delta V2 is 8 squared divided by R is 32. P2 is 2 watts, and this is also equals to P3. So what is the power supplied? The power supplied is the total voltage, the potential difference of the battery, times the total current. So P supplied equals to delta V is, how much is the potential difference? 16 volt times 0.5. Then P supplied equals to 8 watts. Now notice that the power supplied equals the power consumed. P supplied equals to P1 plus P2 plus P3. So this is 8. This is 4, 2, 2. Any question about this problem? 2185 reads the following. What is the potential difference reading in the circuit shown in the figure? Assume an ideal voltmeter is used. Okay, so I explained the voltmeter and the ammeters and other problems that will be posted as well with this video. From previous session. Fifteen, 5, 7 ohm, V 18 volts, five, two. Okay. So how can we calculate the readings for the voltmeters? Number one, those voltmeters are ideal, which means the current going into the voltmeter will be zero. This voltmeter is not going to consume anything from my circuit and now should be treated as an open circuit. So the only purpose of this voltmeter is to measure the potential difference between those 2 points, which means if I know what I'm doing, I can remove this voltmeter and I can substitute it with my potential difference that I'm interested to find, which I'm calling here delta V1 between those 2 points. That's it. This voltmeter is not going to do anything for me in the circuit. It's only an indicator to where I should be measuring or calculating the potential difference. So let's rearrange this circuit, and I want you to pay attention to what I'm going to do right now. I have 7 and 5 in parallel. The resulting resistor is in series with the 2 ohm. So if I am to redraw the circuit, this is 5. I have here 5 and 7. They're in parallel. And then the resulting resistor is in series with the 2. So if this is, so again, since I rearrange, I don't want to lose track of my potential difference that I'm interested to find. I want to find. It is this one between here and here, and it is called delta V1. So in this case, we need to calculate the total current. Let's calculate the total current. I'm calling it I here. Then I will call the equivalent of this as R equivalent 1. And R equivalent 1 is indeed 7 in parallel with 5. And R equivalent 1 is 2.92 ohms. Then this R equivalent is in series with the 2. I can call this R equivalent R equivalent 2. Then R equivalent 2 is R equivalent 1 plus 2. R equivalent 2 is 4.92 ohms. And now R equivalent to 3 would be R equivalent 2 in parallel with 15. Fifteen times 4.92 over 15 plus 4.92, right? Then this is R equivalent 3. The R equivalent total is R equivalent 3 plus 5. So this one is 3.7 ohm. This one is 8.7 ohm. Then I is the voltage, 18 divided by 8.7. I is 2.069 ampere. So this is the current. This is the total current, right? Now, if you multiply this total current with R equivalent 3, you are going to get the potential difference delta V2. That is across the 15 and across R equivalent 2. So if you take this current and multiply it with the R equivalent 3, you get delta V2 as R equivalent 3 times I. R equivalent 3 is 3.7 times 2.069. This is delta V2. Delta V2 is 7.66 volts. So I got delta V2, which is the same across the R equivalent 1 plus the R equivalent plus, which is the same across the R equivalent 2. So delta V2 here is the same. Delta V2 here is across the 15 ohm and also across the R equivalent 2. So if I multiply this delta V2 now, the one that if I divide this delta V2 by the R equivalent 2, I get the current that goes in here. Let me call this one I2. So by multiplying the total current with R equivalent to 3, I got the delta V2. Now, since I have the delta V2, and this delta V2 is across R equivalent to 2, then if I divide delta V2 by R equivalent 2, I get the current I2. Then I2 is delta V2 divided by R equivalent 2, and I2 is 7.66 divided by R equivalent 2, which is 4.9. I2 is 1.556 ampere. Now, if I multiply this current I2 with R equivalent 1, I get delta V1. So delta V1 is this current I2 times R equivalent 1. Delta V2, delta V1 is I2 1.556 times R equivalent 1, which is 2.92. Then delta V1 is 4.54 volts. This is delta V, which is the potential difference. The voltmeter is reading across those two resistors, 5 and 7, that are in parallel. Next question is from the textbook, question 21, 28. This question reads the following. What are the readings of the voltmeters and ammeters in figure 2140? Assume two significant digits in the resistance values. Okay, so this is very important question because here we have some instruments that we need to know how to deal with. I have two circuits. One of them is, this is a voltmeter here, 100 ohm, ammeter here, 15 volts. So we start with circuit A. The ammeter, as I mentioned to you in the announcement, is an ideal instrument, which means this ammeter is not going to have any potential difference across it. It will have a zero resistance. It will not consume any power, which means I can remove it this way. However, I need to measure the current in this branch, so I'll put here current I. Same thing for the voltmeter. This voltmeter is acting as an open circuit, which means does not consume any current. The current entering here is zero. There is no current consumed by this voltmeter, ideally, which means that I'm interested in calculating the potential difference across the 200 ohm resistance, which means I can remove it if you want and replace it with delta V1. I want to calculate this potential difference. Now, always remember, if you have a current going in this direction, the current is assumed here to enter the positive terminal, leaves the negative terminal. For resistors, if you know the direction of the current, then this current will enter the positive, leaves the negative. So I need now to calculate delta V1 and I for that circuit. How do I do this? Well, if I want to calculate I, then the first thing to do is to find the R equivalent, that this 15 volt is across, which is R equivalent is the 200 in series with 100 ohm. So R equivalent here is 300 ohms. Then what is the current? Current is 15 volt divided by 300 ohms, and I is 0.05 ampere. So this is the current the ammeter is going to read. I need the delta V1. Well, now I know the current. This current is entering into this 200 ohm. Then delta V1 is 200 times I. Delta V1 is 10 volts. So this is circuit A. Now let's move on to circuit B. Circuit B is the same, has a few voltmeters and ammeters. So this is my voltmeter, one of them, across the 100 ohm. This is 150 ohm. This is 25 volts. This is 220 ohm. I have an ammeter here to measure the current through this 300. I have a voltmeter here to measure the voltage across the 300 ohm. So, as I said, I can replace this one where I have the current here going in this way. Then I will come back at this point here. So I will put my delta V, let me call this one delta V. I have it here, delta V3. I have it here across the 300 as delta V2. And the ammeter here, I need the current in this branch. We'll call this one I2, this one I1, and of course this also is going to be I1 because it is the current that's going to split into the 220 and 300 and recombine again. So this is I1 and this is I1, right? Okay. So how much is the current I? At the beginning, we need to calculate the current, the total current I. I need to find the equivalent resistance. So start first with this one. This is, those two are in parallel. So I will call this one R equivalent 1, and it's going to be 220 times 300 divided by 220 plus 300. And this is only for two resistors. For two resistors, I can use this expression. Then R equivalent 1 is 127 ohms. Then if I want to calculate now the R equivalent total, it will be R equivalent 1. What else? The 100 is in series with R equivalent 1, and the 150 are also in series. Then R equivalent is 377 ohms. So now, if you look at the equivalent circuit I found, it's going to look like this. 150, 100 are equivalent 1. So now I1 is 25, the potential difference that is across all of them, divided by our equivalent, which is the total resistance, and I1 equals to 0.66 ampere. Okay, so I found this current. Let's go back to our circuit to see what we need to find. All those notations we put. I need delta V2, I need delta V3, right? So delta V3, now I found the current I1, so delta V3 will be as shown, I1 times 100. Then delta V3 equals to 6.6 volts. This is what the voltmeter is going to read. What else? I need delta V2 and I need also I2. So what is delta V2? Delta V2 is the potential difference across both resistors that are in parallel. Because they are in parallel, then they have the same potential difference, which means when I calculate delta V2, I have to include the equivalent resistance. The equivalent resistance of 220 and 300. So I have delta V2 equals to I1, which is the total current that is going through the R equivalent 1. Delta V2 is 8.4 volts. Now I need the current that goes through the 300 ohm. Now I know delta V2, that is across 300 and 220. Then I can calculate I2. Then I2 is delta V2 divided by 300, and I2 is 0.028 ampere. Any question about this problem? No questions? Then we'll move to the next one. Any two parallel resistors will have the same potential difference. They are in parallel. But the point here, you have to be very careful when you calculate this potential difference. You have to include the equivalent resistance. The equivalent resistance, like what we did here. Question 2159. So parallel resistors, they have the same potential difference. Series resistors, they have the same current. So also be careful. Series resistors, they have the same current. Question 2159. Reads the following. In figure 2160, what is? I have the circuit. $250, $150, 350, 550, 35, A. The current through the 150 ohm resistor. So in order to calculate this current, again, this current that I'm calling here I is also going here as I, right? So the same thing here, I will find the equivalent resistance for the 350 and 550. I'm going to call it R equivalent 1, 350 times 550 divided by 350 plus 550. Then R equivalent 1 is 213.89 ohms. R equivalent total is this R equivalent 1 in series with 250, in series with 150. R equivalent is 613.89 ohms. Now the total current, after I found the R equivalent resistance, now I can calculate the current, which is 35 divided by R equivalent, and then the current is 0.057 ampere. This is the current that goes through the 150 ohm resistor. This is A. B, the potential difference across the 250 ohm. Now notice the current is entering this way, that's why I will put the plus here, minus here, and I'm going to call this one delta V1. Then delta V1 equals to 250 times I. Delta V1 is 14.25 volts. C, the current through the 35, the current through the 350 ohms. The 350 ohms, this resistor, I'm calling this current I2. I need first to find the delta V across, so let me call this one delta V2. Notice the plus and minus I put. Delta V2. This delta V2 is across the 350 and 550 because they are in parallel. Then when I do calculate delta V2, I have to include the equivalent resistance. So in this case, delta V2 equals to R equivalent 1 times I, which is delta V2 12.192 volts. Now I can calculate the current. I2, the current through the 350 is delta V2 divided by 350 ohms, and in this case I2 is 0.035 ampere. D, the electric potential at point A, assuming zero electric potential at the negative terminal of the battery. So this is another important question here that you need to pay attention to. Here it is as if I have put the voltmeter, I have put the black probe right here. So this is my reference, 0V, and now I'm measuring with the red probe, and I put it here right on A. Now I need to calculate this potential here at A. How do I do this? Now notice that this potential difference, I call this one plus here, and in green I can say, before I do this, let me see here, I have delta V3, assigned it to across the 150, and then delta V4 between the A and the 0. So for me, in order to calculate delta V4, and as you can see, delta V4 here is the summation of delta V3 plus delta V2. So let me do it this way. So delta V4 is VA minus 0. And delta V3, if I call this point B, delta V3 is VB minus 0. However, I know delta V3 is the current I times 150. So delta V3 I times 150, delta V3 is 8.55 volts. What about delta V2? Delta V2, I found it to be delta V2 to be 12.192 volts. So delta V2 is also VA minus VB. Right? So VA minus VB is delta V2, it equals to 12.192 volts. And I know here that this is also VB. Then take this one, substitute it here, then I have VA minus VB equals to 12.192, or VA minus 8.55 equals to 12.192, and VA is 20.74 volts.